And we are live. Now I wanted to finish the lighting thingy with the diffuse lighting. Like today. So we got the monkey, everything, we got the monkey like lit up, everything is cool. What happens when we scale the monkey? Something strange happens. Negative scale is never a good idea. But what if I do this? And then I do this. Like there is something wrong in here. Like it doesn't change it. It doesn't change. So that's a problem that we need to solve. Oops. So the problem is that totally clear about it, but if I rotate the monkey around the X, I would love to see the monkey lit up right here, thing that I don't see. So oops. So there is something not right about it. I was thinking about it like earlier this day, like this is very wrong. So the normals, in the previous section we pass the normal value directly from the vertex shader to the fragment shader. However, the calculations in the fragment shader are all done in the workspace. So shouldn't we transform the normal vectors to world space coordinates as well? Yes, but it's not as simple as simply multiplying it with a model matrix. First of all, normal vectors, so the problem for if it's not clear is that, okay, the light is shining like that, okay, on the monkey. I simply rotate the monkey, okay, like so. The light should be shining like that, but the monkey is not. So this part should be lit. This part should be like shaded. Okay, that's the problem, because we are using our normals here. We are using our normals we are using our normals in model space, basically, while we are doing our calculation in world space. Okay, so we need to transform the normals, but normals are direction vectors and do not represent a specific position. First problem. Second problem, normals do not have a homogeneous coordinate, the W component. This means that translation should not have any effect on the normal vectors. Okay, so this means that translations should not have any effect on the normal vectors. Okay, so if we want to multiply the normal vectors with a model matrix, we want to remove the translation part of the matrix by taking the upper left. So the problem is that normals are directions and are not influenced by translations. Should not be influenced by translations. That's the problem. Those are the two problems basically. Okay. Second, if the model matrix would perform a non-uniform scale, the vertices would be changed in such a way that the normal vector is not perpendicular to the surface anymore. The following image shows the effect of such model matrix. So basically, you have a non-uniform scale. If you apply the same transformation to the normal, well, the normal is no normal. It's not normal. It's not a normal anymore. Whenever we apply a non-uniform scale, the normal vectors are not perpendicular to the corresponding surface anymore, which distorts the lighting. So 3 problems basically. With the fact that normals are just direction vectors, they should not be influenced by translations, and they should not be influenced by like the scaling. The trick of fixing this behavior is to use a different model matrix specifically tailored for normal vectors. This matrix is called a normal matrix and uses a few linear algebraic operations to remove the effect of wrongly scaling the normal vectors. If you want to know, you can read the article. The normal matrix is defined as the transpose of the inverse of the upper left 3x3 part of the model matrix. So we take the upper left 3x3 part of the model matrix, we transpose and we inverse that matrix. In the vertex shader, you can generate the normal matrix by using the inverse and then the transpose functions in the vertex shader that work on any matrix type. Note that we cast to ensure it loses its translation properties and that it can be multiplied by a vector 3. Inversing matrices is a costly operation for shaders, so whenever possible, try to avoid doing inverse operations, since they have to be done on each vertex of your scene. For learning purposes, this is fine, but for an efficient application, you likely want to calculate the normal matrix on the CPU and send it to the shaders via uniform before drawing, just like the model matrix. In the diffuse lighting section, the lighting was fine because we didn't do any scaling on the object, so there was not really a need to use a normal matrix. If we are doing a non-uniform scale, however, it is essential that you multiply your normal vectors with the normal matrix. Okay, so that's basically what we want. With the camera constant, I intend to pass the normal matrix as a constant. So we have, and I think it should stay in the matrix normal. Then HLSL is struct C buffer. HLSL constant buffer alignment. So I can also do something like this. Oh yeah, fantastic, fantastic, fantastic. So the idea is that I can do camera constants. It's like struct camera constants. Then I have the light constants. And then I have the object constants. Try to compile, everything will break basically. Light constants ambient strength, light constants ambient color. Here is light constants. It here. Camera constants, the projection, the view, here object constants dot the model. So okay, if we do this, it's the same. What happens if you scale the monkey? Is the lighting right? Is the lighting wrong? I don't know. I don't really know, honestly. Well. Let's commit, use HLSL wrap struct in constant buffers. Okay, now the idea is that with the object constants we also have a matrix. That's a normal matrix. Object constants matrix, and it's a normal matrix. And I should really learn about the normal matrix. So we need the normal. When we do this, we also need the matrix model, matrix model, and then we just need to compute our normal matrix. How do we do it? Well, we take the our model matrix. So it is the inverse internal function. Then is defined as the transpose of the inverse of the upper left 3x3 parts of the model matrix. The transpose of the inverse of the upper left 3x3 part of the model matrix. It's a word, okay, that means that object word, which is our model matrix from model space to word space. The model view projection matrix, well, we update the view and the projection separately, and then the inverse transpose of 1 if you're using no unit, the inverse transpose of 1. So we invert, so invert, oops, sorry, we transpose the model matrix, we invert it, and then we transpose it I translate a direction vector, does it change anything? If I translate a direction vector, for example our light direction here, I translate it by 1, by minus 1, minus 1, minus 1, so it's minus 6, minus 6, minus 6. Like, does it change anything? Not really. But if I have, for example, minus 1, minus 1, minus 1, and I translate it by 10, so here becomes 10, 0, 0, it changes. So yeah, that's not the same. So I'm not really convinced of this. Because with the transformations you can clearly see that yeah, the translation is something like this. Okay, the rotation gets like this. The scale is something like this. So basically taking the upper for like the upper so taking the transpose of the inverse of the upper left 3 by 3 part of the model matrix is something the transpose of the inverse of the upper left 3 by 3. Taking the upper left 3 by 3, you have the contributes of the scaling, the contribute, you don't have the translation, okay, and the contributes of the rotation. Okay, so the idea is that you just have the contributes of the scaling. So you scale, you rotate, okay, oops, how to compute normal uniform scale. When we stretch a shape along, say, just the y-axis, the y-coordinates of all the vertices oops. So, diagram from this article explaining how the inverse transpose matrix is used for transforming normals. So this gives us a conundrum. The y-coordinate of the vertices needs to get bigger, but the y-coordinate of the normals needs to get smaller. If we neglect this detail, we just use the same model matrix for transforming both the vertices and the normals. The shading we get will be subtly wrong. Things like specular highlights will bunch up on the skinny poles of the objects instead of spreading across the elongated sides. Okay, the inverse transpose of the model view matrix inverse transpose of the model view matrix of the model matrix, because we are doing our calculations in model in world space. What you call the normal matrix here computes exactly the transformation we need to adjust the normals correctly. By inverting it, inverting the model matrix, we undo the scaling, the rotation, and also the translation. By transposing it, we undo the undone rotation. Okay, getting us back to the rotation we started with. Okay. Now we have to calculate normal matrix. So for the normal, we'll scale and rotate. Then we invert. invert, and then we transpose. Okay, and then we upload the normal. We scale and rotate, we invert, and we transpose, and then we update the normal. Okay. When we are doing the lighting, in the vertex shader, sorry, the default, when we are doing the normal, we need to multiply it by the normal matrix. So we take the normal matrix, we take our normal and multiply it by our normal matrix to get the normal we want. Yeah, it kinda works. Oops. Yeah. It looks like it's working. I'm surprised. So inversing matrices is a costly operation for shaders. So basically we don't want instead of working with 3x3 matrices, here we just work with our matrix, which is a 4x4 matrix, and just use the scale and the rotate, since the translation is useful for it's useless. It's not useless, it's incorrect for normals, because they are direction vectors, and direction vectors should not be translated. Now we have the scale, we have our scaling, we have our rotation. No translation applied. We multiply them, combining the two transformations. We invert them, so having the inverse transformation, and then we transpose, and this supposedly like fixes it, fixes that the thing about the rotation matrix. I don't know. I should we should like look at the math here, but like let's take the definition for granted, like at least for now, and check whether or not it's working. And I think it is working correctly. Just rotate. Obviously, allow me to. Yeah. Yeah. Okay. Like I wanted to finish this today so that we can do something more interesting tomorrow. We got our lighting, our ambient and our diffuse lighting with the sun basically, and tomorrow we'll do something else. I don't know what. I'll probably need to like go through the code base again to fix some to-dos that I left behind from the mouse thingies. Okay, it's getting late. Bye bye, have a good evening.